Any robot, for it to finish its mission, I try to think of it as like answering three questions in a loop. Where am I? What should I do next? And is it safe? So if you answer these three questions in tandem, continuously, you should reach the goal. Yeah, good evening, everyone. I was going to talk about some of the work that, I won't say this is the work that we have been doing at our robotics startup, but probably largely general stuff that could apply to most robotics companies or robotics products that you're trying to build. There is, I kind of give a fair warning that there is zero AI involved in this. It's all classical, probably stuff that has been done like 30, 40 years back. Nothing groundbreaking. It's just that some concepts I thought we will share, and I'll keep it as informal and interactive as I can. It was meant for a slightly different audience, and I am happy to pare down as much as we need to, and we can skip some portions and we can spend some time on more portions, and depending on what is of interest here. So you can, it's a little pompous saying that software architecture in most autonomous systems will look like this. I would argue that mostly the architecture would look like this in any kind of robotic systems that you're thinking of, whether it's ROS based or whether it's something proprietary, whether you do drones or underwater robots or mobile robots, doesn't matter, but they will ultimately follow a framework that is close to something that looks like this. So what does it do? Any robot, for it to finish its mission, I try to think of it as like answering three questions in a loop. Where am I? What should I do next? And is it safe? So if you answer these three questions in tandem, continuously, you should reach the goal. That is the overall premise of it. As I said, like all robots, this should apply. And the focus of today's talk is, where am I? We're not trying to do the other two, which is 3 is more like perception, computer vision, and so on. And 2 is more like motion planning. We're not talking about that. We're talking about what we call as localization. That is localizing in the environment in which the robot is operating. And we'll just look very quickly at the whole architecture. It's what we call as a pub-sub model. There is a bus, and different modules are publishing things, and different modules are picking topics from there. Okay. And the localization module arguably is picking things from the sensors. Sensors are the ears and eyes of the robot. It's going to tell where it is. And also it could have a pre-built map of the environment. In our case, that is generally true, where we will have a map of the factory in which we are operating in. People like Waymo, that is definitely true. They are doing extensive mapping of the neighborhoods in which they are operating in. I heard that they just got the go-ahead for Palo Alto. They've been in San Francisco for a while. Now they've moved to Palo Alto, and they're like mapping and getting this HT maps and so on done. Tesla is famously bullish about it and say that we don't need a map and we will go wherever we are and so on. But, to each his own. But I think with the pre-built map, it's a much easier problem. Without a map, it's a harder problem. Solvable, but harder. So it will tell where the robot is. This model is supposed to tell where the robot is. Then the motion planner will pick it up and say that. Then there is a global mission planner, which will say where is it that you need to go. But there is something that I wanted to talk about before going into it. And this is true with almost all robotics companies. There is this notion of, this is the loop. See, understand, plan, move. That's the loop that you want. And we are like somewhere about understand. Where are we? That's the part that we are trying to focus today. And the focus is on probabilistic approaches. So on why are we saying probabilistic and not deterministic? Because there is uncertainty in both the robot's motion as well as the sensor. So this is in general true. We should think of it in a probabilistic terms for both localization as well as tracking. Whether the question, where am I, is also probabilistic. The answer is probabilistic. Am I going on the right track is also probabilistic. Okay. So to give you a flavor of what that means is, say this is a drone and you're like trying to track it in 3D. So it's somewhere in 3D space. We don't say that drone is exactly here. We say drone is likely here in a uncertainty bubble. And this becomes like super important to make this distinction right away. And I'll just give an example of what this means, right? Like, why are these sensors observed? What I mean by uncertainty. So anything that you measure, the odometer or the camera or the IMU or the LiDAR, even if it's the most expensive sensor that you can put in there, it's likely that they're all making a mistake in the measurement. That's just the nature of it. It's a physical sensor. There will be some kind of noise. You have to make peace with it. The other thing that you have to worry about is that you might ask this robot to go at a certain speed, but did it go instantly? Probably not. Motors are also physical devices, and they will also take some time to ramp up. So both these things, if you put together, it's a bit of a fuzzy nature as to where the robot is and what that action is that you're asking it to do. And this is something I'll quickly go through. You see that this is Model 3 sensor placements. They'll have they're camera driven. They have 8 cameras around it. They have ultrasonics, they have radars in the front. So what I wanted to show you was the perception cone as to how far the vehicle is able to see, right? Different sensors have like different ranges, narrow, wider, long, short, and they are actually trying to understand that environment by fusing all these different sensors. Okay, that is the fundamental thing that they will try to do. But this is true with all of them. Waymo has an even bigger suite with even more cameras. They have a 3D LiDAR. They have everything. So, different sensors have different characteristics. For instance, camera is like fantastic if you want to make sense of things. Is there a person sitting there? Is there like an object that is there? Is there a road sign? What does the number say? 50 kilometers per hour is the speed limit that you want to know. That's the only sensor that will tell you that. Radar is great for working even in snow, rain, fog. I mean, it can be completely dark and they can do it because, it came from defense and it works very well. You can also understand how fast that object is moving. That's the only sensor that will give you. LiDAR has the lowest noise floor. So it is an expensive sensor, but it is very easy to handle. Noise is very low and you can work in pitch dark and so on. So they all have their own good properties. Some of them are costly, some of them are cheaper and so on. But the idea is like, how can you use them all together? That's the whole idea. And exactly like Vijit was talking about, what if you're in pitch dark, then the camera is useless, then you have to rely on something else, right? So I don't know whether you guys saw that Waymo video recently where there was a person who just fell and it just quickly swirled around. Yeah, it was very cool. So this is the idea. Like, what would it look like, right? It could look like, we're fusing different sensors. You want to set, say, like a quad tower like this. You have a drone and you have multiple motors, and each motor you want to set a set point, how fast they should be going. So the feedback loop is actually driven by some sensors. And multiple of them. It could be camera, IMU, GPS, altimeter. And you fuse them and you find the new state. And then that goes into the controller. So that's what you want to do because now we are motivated enough to understand that there are different sensors you have to use. And those sensors, they have their own problems and we need to fuse them. Now starts the talk. So we are motivated so far saying that sensors are noisy, but we have to deal with multiple of them. Now the question is how to combine multiple noisy measurements. Okay. So I'm starting with a toy problem and we will try to answer it by the end of the talk. Say you have 2 thermometers, nothing to do with robotics, but it's easy to understand with this problem. The person who taught me Kalman filters started with this example and that stuck with me. There are 2 thermometers. One is probably expensive because it has lower standard deviation and another one is cheaper and has a higher standard deviation. And a particular person was measured 101 degrees on one and on thermometer 1 and 98 on the thermometer 2. Now the question is, does he have fever? And that's the question that you're interested in. Obviously, you want to know what's the method to even combine it. Can we average it? Is it just 98 plus 101 by 2? Is the combined reading better than the individual reading? Is it better to just throw out the shitty thermometer? So those are the questions. And you can see that there's a parallel to the sensor world as well. That's what you're trying to answer. So I just want to do one clarification and move on to robotics again. How do you measure standard deviation? What would this mean? So the idea here would be that they would have calibrated it. The manufacturer would have calibrated it. If they don't calibrate it, then you have to calibrate it. So you take a known temperature and then you take like multiple measurements of it. And over a period of time, you see what was the variation from the ground truth. And you average it out and say that's the standard deviation, which means that if the real temperature was 100, then this guy can give you anywhere between 97 to 103. That's the first standard deviation, but it's a Gaussian. So it can give 108 also, but the chance of that is very, very low. So it is most likely it will be in that band, 97 to 103. This one would, on the other hand, will give you 99 to 101. It's much more narrow. Yeah, much more precise. So we'll take a look at some sensors and then we'll come back to this topic. So one sensor could be GPS or a radar altimeter. These are commonly used in drones, drone world, especially if you're outdoors. GPS is a very cheap, very reliable sensor. Obviously, we are now, it's fairly normalized for us. We turn on the GPS everywhere we go. It's, again, we can thank the military for this. So it's an absolute sensor. It gives you the lat long wherever you are in this planet, as long as there is constellation and you can cover it. But the measurement error will be of the order of several meters. Need to be wary of that. But error will not compound. So you get a GPS reading, say you just got like 2 or 3 satellites, reading is bad, no problem, you take some more steps, clear sky, you will get a better reading. There is no compounding error, which is a good thing with GPS. So a radar altimeter, same thing. It's like you send radio waves, it will bounce off the earth. So you will know exactly, based on the round trip time, you will know exactly how high the drone is. Again, an absolute sensor. So on contrast, you'll also invariably, we use IMU a lot, initial measurement unit, gyroscope and accelerometer. In fact, I'm sure all of you are using gyroscope and accelerometer. If you have a smartwatch, that's accelerometer, that's what is measuring steps. If you have auto rotate turned on in your smartphone, that's a gyroscope. So what it does is, literally these things are called MEMS, micro electromechanical systems. These are small chips that come in most smartphones and whatever you have. The way they work is that the accelerometer will measure acceleration on the rigid body on which it is mounted. Think of it like some rigid mass which is suspended by springs. So if you pull it, just by measuring the displacement of that spring, you will know what is the acceleration that body is being subjected to. And why is that good, right? You know that gravity is always G. Okay. Now, if I do that and I have a accelerometer mounted on it, you can resolve it and see that this is the force that was acting on me on the X direction. So Y direction is always G, that you know. So you can find out what's the force on me in the X direction. So acceleration is easy to find on the other direction, which is not G, which is what you want from your calculating acceleration on the robot. Gyroscope is the same thing, but angular velocity. You want to see how much the robot rotated. But you can see that there is a problem here. There you are getting absolute position. Here you are getting a second derivative of position, only acceleration. So you have to integrate it, and as soon as you integrate it, you will have noise. And that is what is shown here. Accelerometers, in general, these things have a lot of noise. So you'll see that accelerometer noise is very high frequency. There will be a lot of noise here. And gyroscope tends to be low frequency noise. It will drift slowly over time. And there are techniques to combine the two, which they call as complementary filters. You'll use a low pass filter for the accelerometer to get rid of the high frequency noise, and you will integrate it with the gyroscope with a high pass filter, and you can get angle and you can get angular velocity. So these are called complementary filters, and they've been around for, like, as I said at the top of the talk, 25 years or so. Nothing. This is like just a slide I had on camera. I'm not doing too much camera here. You can see that this is true with a lot of robots, not just drones, but Aruko markers are fairly common, where you can put like fiduciary markers and use that to hone in on where you are. For instance, drones, when they tend to hover, they can drift a lot, or the position can change. So if you have the hovering spot, they tend to put like Aruko markers, and you can find out what is the horizontal shift. If you're tracking that Aruko marker, and you can see that there is a shift. And if you're just using an IMU, it tends to drift. Just GPS also, because there is just noise and it will drift. So it is good to have these kind of markers, and you will know where exactly, if this is moving, and you will know exactly how much you're moved and stuff like that. It's just an absolute marker that you have created now. So these patterns are not random. Nicely rounded rectangles are actually very useful. They are grids, they are converting into grids, and you know exactly how far you are and things like that. Wheel encoders for mobile robots. How does this work, right? Like, what happens right now is that there is a shaft, and the shaft you will place an encoder like this. Way to think of it is like this particular spot, right? If you're moving without slipping, the key idea here is that this point, how much ever this point moved in space, that is equivalent to this point moving in space. Does that make sense? Angularly, how much that arc is the same as linearly how much that wheel translated. So that is the fundamental idea that they use. If you're slipping, which means that the wheel just slip like this, then this is not true. You should rotate freely. Then you can say that, you can make the claim that I'll measure how much this one moved, that rotation, and that I will translate to S, which is linear. I'm interested in linear. I don't care as much about angular, but I'm interested in linear. But how much did that robot move linearly on ground? But there are issues with it. In general, you will see that, say, the blue line and the orange line is a good example. It is very, very good, these odometer type of sensors, very, very good in short bursts. But if you it's a speed. So you have to integrate to find position. So if you do it over time, you can see that the orange one is what it's predicting and the blue one is what it actually did, and it has drifted away. So it's not something that you should do for too long, but you can use it in bursts. So as I said, every sensor has its own pluses and minuses. The last one in my list, this is a LiDAR. This stands for light detection and ranging. Our corner piece, this is what we mainly use in our product. There are people like Musk who have been bullish about it. They say that you don't want to use a LiDAR, it's for idiots and all. But this is generally a good sensor because I wanted to show you what it does. So this room, you can see that it is mapped like this. Except for the part where the ball is and it is occluded, you get the entire room and you can make sense of it. It's, as I said, low noise floor, independent of ambient lighting. We have run our robots completely dark and it will find its way and it will do like hours together, it will work. So those things are nice. And you can, if you look at 3D, this is like a bicyclist. We are tracking that bicyclist. I want to show that. This is a bicyclist. You can see that guy, the profile is very nice. You can actually see that it's a bicyclist and there are trees, there is a road. You can go around him. You can see the cars that's right next to it. It's very rich and you can see the whole thing. So this is a 3D imaging of your environment. And what you see is what you get. Unlike a camera where the whole 3D is projected onto 2D and you need to make inferences on it. So now what happens is that in the 1D case, 2D case that I was talking about, it's just operating in a single plane. It's rotating like that. Now the 3D case is that you have 16 such rotations that's happening in space. So it is like a cone. It will rotate the whole around you, okay? And you will get the entire profile. This is one, I will not spend a whole lot of time on it, but I wanted to give you some motivation on the map, and there are some examples around it. Say you have a wall like this, like a room like this, which has walls like this. The LiDAR scan, right, across the beams, it will look like this. And it is hard to make sense of it, but you can imagine if the robot is here and it is actually the beams are hitting around the room, right? You can see that this portion of the wall will be farther away and this portion of the wall is the closest, okay? These two walls are not even seen by the LiDAR because it is on the blind spot. And how do you use the LiDAR? Okay, this is all great, but how do you use the LiDAR, right? And if you see how we use it, this is the answer. Say you have the map of the room, okay? And you know where the wall is. And now say the robot has taken a step closer to that wall and probably even slightly to the side. That wall is going to appear closer. This wall is going to appear closer. Now, if I look at my reference map and what my current reading is, I'll know exactly how far I have moved towards this wall and towards that wall. That's all there is. And similarly, if the robot is just rotating, these two walls would look rotated this way. Okay, that's what the robot is reporting. Of course, the walls are not rotating, only the robot is rotated. So you can, with your reference map and with your current reading, you can tell how much exactly that robot has rotated. So that is the idea behind using LiDARs. Now you can understand why LiDARs are attractive. LiDARs are attractive because you can tell how far this wall is within a centimeter or 2 centimeter accuracy or 3 centimeter accuracy. None of the other sensors will give you that kind of accuracy. So what that means is that, say, if the robot has moved 10 centimeters, you are within plus or minus 2 centimeters the estimation of how much the robot has moved, which is great. That's why you pay the big bucks for LiDAR. Okay, this is one fun example. So say there is a robot and that robot is walking along a wall and that wall has 3 doors. Okay. And we want to understand where that robot is. That is the problem. It's a toy problem, very famous, came in Sebastian Thrun's textbook many years back. So Thrun's textbook, which he wrote like 20 years back, and after that he's an entrepreneur and doesn't do anything mathematical, but back then. This is a very good example, I think. So first you have zero idea where the robot is along the wall. So that's why the belief in where the robot is all flat, because he could be equally likely along entire wall stretch. Now he keeps walking, the robot keeps walking, and one of your sensors told that there is a door, just told there is a door. But because you had the prior map, you know there are 3 doors. You still don't know which door. So there are 3 blips saying that he could be in front of the first door, second door, or third door. Now, the belief is, the new belief where you think is a robot is this measurement that came from the sensor times your original belief of the robot. So if you multiply these two, you get the new belief where that robot is. Now the robot continues to move. Because he is continuing to move, there is some uncertainty. You don't know where, if the odometer is good enough or not, and your belief is fading out. And that happens here, right? Like you had a slightly peaky belief where you are, but as the robot continues to move, the beliefs start to get flattened out. And if the robot takes enough steps, that will become all flat. But now it's like that. Now the robot says that I'm seeing another door. Again, if you see a door, that means that you are in one of the 3 spots. But your current belief is different. You have like these small peaks and you have these new peaks. You multiply these two, you have something that is very, very nice, which says that the robot is in front of the second door. The idea that the robot within 10 steps reported 2 doors, that means that there is no choice, but the robot has to be in front of the second door. So that is the fundamental way in which we use multiple sensors. So this is an example that he uses, and it's famous to quote this. Okay, let me formalize it. This is probably the math that I have. Say the robot state is a position in the XY grid and an orientation, the way in which it is oriented. And the control that you give is like some linear command and an angular command. The robot states, you don't know, they're hidden, and you have access to some observations, LiDAR scans or some kind of sensors you have. What you're interested in is like this belief distribution. I told it's a distribution, it's not an exact thing. So what is your belief that the robot is at a state psi I? Okay. Given that you are going to give a control of you and the robot's previous states were this. Okay. And one of the key ideas here is that if you assume it's Markovian, which means that the robot's current state depends only on its previous state and the current control and nothing else, then there are some good things that will happen. And the way to think of it is that if the robot is here and I give it a push, what is the belief that it will go here or wherever? Okay. I don't care if the robot came from the left side or from the right side or it came straight. I don't care about it. Now that the robot is here, all I care about is what is the control input I am giving. So that's why Markovian is an okay thing to assume. And a lot of robotic stacks, you will see this Markovian type of assumption. If you do that, okay, and now you also add the map into the picture. There is also the map that you have built, correct? Then this belief distribution, which we call the posterior, will decompose into 2 nice quantities. One is the probability that the robot is in this state, given the previous state and the current control, times the probability that the robot saw a particular observation, given the current state and the map. So this is what we call as the motion or the prediction model. So if you give a certain input, this will be the output. That is a motion or the prediction model. And this is what we call the observation or correction model. You are predicting that the robot is going to go in a certain way, but what is the sensor telling you? The sensor will say that no, that doesn't seem right, and you need to refine your estimate. So that is the observation model. That could come from any sensor measurements, and this could come from your models of the way you have constructed the robot. Mechanically, you would have a unicycle model or a bicycle model and so on. Like whatever the way you have constructed, you can predict. Like if this is the input you give, this is the output. Okay. So you can see that this is a nice way to recursively refine your belief. And now you can go back and see that example where the robot is walking along a wall. This is the way you are correcting yourself. You will make a coarse prediction and then you will make a fine correction based on the sensors. And you keep doing that, hopefully you have a decent understanding of where the robot is. So this is one slide on Gaussian. Everyone knows Gaussian maybe, but I usually have this. So Gaussian distributions tend to describe physical sensors very well. There is it looks like a bell curve, and there is a mean and a variance that you will tend to crack. So what does mean mean? So what is the average measurement that particular process is going to tell? And it could be, if it is very thin, that means that it's very precise, the noise spread is low. If it is very thick, if it's very fat, that means that the noise spread is much higher. So the interesting thing about Gaussian distributions is that you don't need to carry the distribution, you just need to carry these two parameters, mean and variance. With that, the distribution is completely defined. And this is where we come to Kalman filters. And this is the concept that blew my mind when I learned robotics. I still think it's great. Rudolf Kalman is a Dutch engineer in the 60s. And he was the one who came up with this. A lot of modern flight control systems, missile systems, a lot of them use that. It's like a 60-year-old tech result, so to speak. What he showed was, if the motion model is linear and it is corrupted only by Gaussian noise, and if the observation model is linear and corrupted only by Gaussian noise, you can use this kind of a filtering mechanism to add multiple sensors, where these numbers F, G, H, you will be wondering what does that mean, right? Like all it means is that these things I'm saying that there is a linearity to it. That's it. The relation between psi I and psi I minus 1 and u is linear. Z and psi I is linear and so on. That's what it means. And it's a reasonable assumption. Even if it is not linear, you can linearize it in some regimes. One example, toy example that you can think of is like, say a ball is rolling in one dimension. You are interested in seeing the position, measuring the position, but you can measure only the velocity. Okay. You can measure the velocity, but you are interested in capturing the position. Then you can say that the current position is the previous position plus velocity. And velocity is constant velocity, so it's same. And you are able to measure the velocity. So if you look at it, psi of t, and you augment the state, both position and velocity are thrown in. So the current state is 1101 times the previous state. And the current measurement is 01 of the current state. So F is this matrix and H is this matrix. Very simple idea of what this could be. Of course, for robots, of course, it can be more complicated, but this is the thing. These tend to be some deterministic matrices. So with this in mind, right, what you do is that in Kalman filters, the prediction step, you will just use the model that has been given to you with F and G matrix, and you'll say, this is my prediction. This is where I think the robot state is, given the previous state and given the control. So you have given some linear velocity and angular velocity, you know the previous state, predict it. Don't be shy, just predict it. Now there is a correction step, and this is what we call as the innovation term or the correction step. What does this mean? Z of t is what the sensor is telling you. H times this predicted state is what you think the sensor should tell you, right? H times psi of t is what you think the sensor is telling you, sensor should tell you, right? Like this is noise. So this is where you think the robot is. H times where you think the robot is what you think the sensor should be giving out as a reading, okay? But the sensor is telling something else. Z minus that is the innovation, is what you need to capture in your refinement. That is what we call as a Z. And how do we capture, in what proportion? With something called a Kalman gain. The gain that is like a way you scale that innovation term and you add it to your current belief of the robot's position. You add it. Now, what does this Kalman gain look like? The Kalman gain is something that cleverly balances your, what you think or how bad you think the sensor which is telling you and your current uncertainty. If you are very certain of where the robot is and you have a shitty sensor, then Kalman gain should be very low. And vice versa. If you don't know where you are and your uncertainty is blown up and you have like an awesome sensor which is telling you that this is where it is, Kalman gain will be very high and this one will get completely corrected. So that is the trade-off. I'm not getting too much into the math of it, but that is the conceptual level, that's all there is. You are refining your estimate again and again, but you should know how bad your sensor is. That calibration is in your hands. If you know how bad your sensor is and you characterize it, you will get very good results. This is proven to be optimal. This is an outcome. So thermometer, which said that we had a shitty thermometer plus or minus 3 degrees and a good thermometer plus or minus 1 degree. Okay, and the standard deviation is plus or minus 3. So the variance is 9 for one and 1 for one. Now the cool thing about Kalman filter, I wanted to bring it out in this example, is that the way Kalman says that you should add these two thermometers is, sigma 2 square T1 plus sigma 1 square T2. So you go after the other guy's standard deviation and do it, right? So you place a 10% weight on the shitty thermometer and a 90% weight on the good thermometer, which is intuitively correct, okay? And you're saying that the true reading on the person is 98.3. It's not 98, but it's 98.3. But how does it make sense? 98.3, is that correct? Okay. You can also say, what is the uncertainty of this? That is 0.9. Instead of 1, now it is reduced to 0.9. And this is a great result. I don't know if I will do that or not. You will appreciate this or not. Let me try. Even if you have a very bad sensor, it is saying that the uncertainty is dropping strictly. So so that was one of the questions that we had asked, saying that, hey, why don't we just take the 98? What is the point of taking this 101? You know it's a bad sensor. Why are we taking that? So what it's saying is that strictly, if you know how bad the sensor is, then strictly you will get a better result. Now you understand, even when you're combining a $5 IMU with like a $4,000 LiDAR, you'll strictly get a better answer. Okay, now we'll quickly finish mapping and then move on. So this is like ISE, and this is like a road in ISE, and you can see this is the OpenStreetMap. And how does the map look? That is a question. So what we did was, this is like a break that I had taken, and I was at ISE at that time. We fitted a golf cart with like an autonomous stack, and we did a mapping run. And how does that look like? Question. It'll look like this. It is not any glamorous thing. It's a very high resolution map. So at this scale, you will not appreciate the details. But what has happened is that you go from one side, we went all the way up there, took a U, came back. There's a parking lot where you did multiple rounds like this, and then came back, crossed over, and came back to the starting spot. So I am like placing some emphasis on these spots. These are important points where you know that you crossed in real life, okay? When you are generating the map, you need to correlate where you crossed in real life and where you are actually saying that the robot went. Is that clear? Okay. Now your question is like, this is a slightly older map. You can clean this up also. Wherever you have like density less than some threshold, you can just clean it all up. But sometimes we don't do it blanketly because there are some good features. But this is the key idea. You can see that there are walls. There's a building and these are walls. The map itself is in 3D. You'll not see it, but the walls are rising and you can see this in 3D. You're just looking at the bird's eye view of it. Okay. But what I wanted to tell was very simple stuff. So when we came back to the spot where we started, which is important. And similarly, here you can say that it moved back and then came back here. So this place, we crossed this point multiple times. This is important checkpoint while doing the map. So far we have been talking, if you have a map, how to decide, how to know where the robot is. But how do you even generate the map? How do you know it's a good map? Okay. So that is what we are doing now. So the map itself, as I was telling, is just a grid. If you have like a OpenStreetMap or whatever, and if you want to represent it, it will look like this. It's just a 2D array of zeros and ones. In practice, it will not be 0 and 1, it will be some number between 0 and 1. It's probabilistic. Okay. If you have a room like this, right, as I was telling, this is the way the map would look. Wherever the walls are, you will shade it out. And wherever you have free space, the robot will say that's all free. But there are issues around it. Like, how do you generate it? If you have sensor noise, if you have a highly noisy sensor, you can get a map like this, which is no good. It can be fuzzy. Okay. It can be worse than that. If you have a long, narrow corridor, you can also have ghost walls. The same wall can come multiple times because what do? The robot will take a narrow section of the world it is in, put it on a grid, then take another step, and then it will discover more of the world, put it in, and keep doing that. Now, if you make a mistake, you say that the robot actually went like this, but say you actually did that, the walls will shift, and you will insert that wall as is. Then you will get ghost walls like this. You get very thick walls. Then you don't know where. Then if you use that map to localize, you don't know where you are. You'll make that kind of a mistake, right? Ideally, the wall should be almost 1 pixel. Then you know that it's a good map. Okay. how do you solve that? You solve with Kalman filter again. Kalman will help us. So what happens is that every time the robot moves, right, like the robot makes a stationary observation, you insert it in the map, okay, and then it moves, you use your prediction model, and then you use your correction model, and then we say, okay, that is the final position. Now you put the new wall in, and you keep doing that, and then you will get like a final map. That's the idea. But there is still one step I'll tell, and that's where my talk ends. You still are not guaranteed to be correct, because this can be a kilometer long search and so on, and it is not guaranteed to be correct. So what preserves the sanity of this map is what we call as loop closure, meaning you have to come back to some known spots again and again, and also tell the robot that you're coming back, you're revisiting the same spot again and again. And how do we solve that? Something like this. So from the Kalman filter method, you can get like these triangles, which is where you think the robot is, okay, and you have a sequence of positions where the robot went. It went from position 1 to 2 to 3 to 4 and so on, okay, and it did that. Now there is a constraint, right? Like this is the distance that the robot traveled from position 1 to position 2, and this is the orientation change that has happened. But in addition, you're also giving these red constraints, which are the loop closure constraints, saying that 4 is exactly the same as 1, or it's very close to 1. 8 is very close to 2. Because, how do you know that? Because you did it. Okay. So either the robot recognizes that the loop was closed and it will actually add that constraint in, or you have to manually key it in. But without this now becomes like a graph pose optimization. And you can, what it says that the triangles are all the nodes, and the edges are all the constraints. So think of it like a bunch of balls. It's like a spring, and you have to shake it up so that the right positions are held, right? Like it's a minimum energy type of problem. So it is like a optimization that you have to solve. Once you solve it, you know what are the true poses that the robot went during map construction. Once you know that, it's easy. Wherever it went, at that time, whatever sensor measurements it saw, you just insert it into the map. And that's it. You'll get a true map. So that's all I had. Maybe one last thing, talking about Shackness. So he has like a way to find out what it is. This is like what they call as particle filter. It is kind of, it's still in the same family of Bayesian filters. He doesn't know where it is. The robot doesn't know where it is in the museum. Okay. Actually, the robot is doing that. So what it does is that very interesting. It sprays these particles, which is proxy for saying, I am in one of these spots. So entire map is covered. Now it will start moving, and it will start refining where it is. So the robot started moving, and then the particles are coalescing, which is the belief where the robot thinks it is. Okay. And then it will come to one particle. Now this is very interesting. So there are two rooms. It thinks it is either having to go this way. It's either in front of this room or it's in front of this room. These two rooms are identical, if you will. So there are two balls. It either thinks that you are in front of this room or it's in front of this room. Now, after it got into the room, it realized that it's in this room because it's seeing these kind of shapes. Okay, that's all I had.